onto that value. The top, we'll do something very similar. We have n x to the n, so I've got 1, no, n is, pop in 0, I get 0 plus x plus 2x squared plus 3x cubed plus 4x squared, sorry, to the fourth plus dot dot dot. And I'm just going to assume that's sum. It's a sum s. I'm going to multiply everything by x. And I get, so this becomes, multiply that, that becomes x squared plus 2x squared plus 3x, 2x cubed, 3x to the fourth plus and so on. Now if I subtract, I get s minus xs equals, well, that's going to give me x. 2x squared minus x squared is x squared. 3x cubed over minus 2x cubed is x cubed, and so on, which we just solved over there. Although we're off by a 1 here, so let's see. So if we plug in, no, that's right. So this is just this minus 1. So like 1 over 1 minus x minus 1. I feel like that negative 1 doesn't go there. Oh, yeah, all right. Let's do something else there. If I factor an x out, I'm left with x plus 1 plus x squared plus so on. There we go. And that is just s over there, which is x times 1 over 1 minus x is equal to s times 1 minus x. Solving for s, so the sum would be equal to x over 1 minus x squared. All right, let's combine some stuff here. So we now have what this sum and this sum are dependent upon x. So my expected value for, my average value for the energy at some frequency f is going to be hf times x times 1 over 1 minus x squared divided by 1 over 1 minus x, which is hf over 1 minus x, hfx, or 1 minus x. Plugging back in our value for x, this becomes hf e to the negative hf over kBt over 1 minus e to the negative hf over kBt. Multiply top and bottom by e to the positive hf over kBt. On top, my exponents go away, and so I'm left with hf divided by e to the hf divided by Boltzmann's constant times the temperature minus 1. So with that assumption that the energy has very specific values at a particular frequency, now if we plug it into the equation that we had before, we get 8 pi f squared over c cubed df times this times hf over e to the hf over t minus 1. that simplifies-ish. So this is our energy density at a particular frequency, 8 pi hf cubed over c cubed e to the hf over k dt minus 1 df. And this matches what we have right here. The implication, the huge implication, is that energy is at very specific values. For a particular frequency, it's not anything under the sun. It can't go to 0. It can go down to HF, which is a small number, but not 0. And quantum physics is one. Questions? We flip back to that first page, or the second page. Black body radiation, done. Photoelectric effect. Einstein came up with special relativity, general relativity. Photoelectric effect is that final thing that's made the Nobel Committee go, we can't deny him any longer. All right, photoelectric effect. If I take some sort of surface, like a metal, and I shine a light on it, there are situations where the light's going to shine on it. Basically, it'll shine on it, it'll give energy to the electrons that are there, and the electrons will go shooting off. And if I have a detector here, I can then measure a current. Now, what they noticed is that there is a frequency, a threshold frequency, that if light is under that frequency, then no particles get ejected. So let's think about waves as mechanical, think about mechanical waves right now. If you're dealing with a battle rope, that's a long rope attached to the wall and you're putting waves in it. If you increase the amplitude, you're putting more energy into it, less energy, same amount of energy. Yeah. So if light is a wave, and there's a huge experiment done in the early 1800s, Young double slit experiment, that I assume I've talked about this, or was that the other group? Okay, got it. So if light is coming in as a wave, basically it's going to go through these two slits, and then we have points where they overlap. And when I have two waves overlapping like that, what do I have? Flashback to December.
Interference.
What kind?
Deconstructive.
Yep, I assume you said constructive.
Yeah.
Okay, constructive interference when they overlap like that. When one is peaking and one is at the trough, at the low point.
Destructive.
Destructive interference. And so what I would expect if I did this against a wall right here, I would expect there to be alternating bright spots, dark spots. And what you actually end up with is you have the biggest in the middle, and then less so, you get dark spot, another spot. And this was Young's double slit experiment done in the early 1800s. Early 1700s? I think early 1800s they finally were able to do it. So if light is a wave, which it clearly demonstrates right here, then I should be able to just turn up the brightness. It's like increasing the amplitude, and I should be able to eject electrons. But if I'm not above the threshold, it turns out, I can't do it. Not at all. If I'm above that threshold, and I increase the light, I do get more electrons coming off. But I'm not getting more if, I'm not getting more if I'm below the threshold. The analogy I think of is if I need to kick a ball over a wall, I need to apply a certain amount of energy to get it over. If I kick it with not enough energy, that ball's gonna hit the wall, bounce back. No matter how many times I kick it, it's gonna just bounce back. I have to get above a threshold in order to be able to clear a wall. So if you think of light as a particle, if I'm below the frequency, it's like kicking the ball below the energy that I need. And I need to get above that in order to be able to clear it. And so Einstein comes up with the idea that light is behaving like a particle here. Now he acknowledges it does behave like a wave here, but in this case it behaves like a particle. And that the energy of the light wave, H shows up yet again, is directly proportional to the frequency. I'm going to put the little symbol down here to represent the electromagnetic waves. It's really the gamma. And so now, not only does energy seem to be discrete, but it also, if we combine it with the photoelectric effect, we now have this idea that light sometimes behaves like a particle. Well, the next bit, the third thing that was on the list is Compton scattering. Is trying to explain that if I have an atom and I shine light at it, I get an electron go zipping off, and the frequency of the light changes. So I shine it at a certain frequency, an electron gets ejected, and now light bounces off at a different frequency. How can that be explained? So draw my fancy diagram here. I've got my atom sort of zipping around like that. I have a light wave coming in at some frequency. So it's some electromagnetic wave. I say light wave, it could be visible light or not visible light. It's just some electromagnetic wave. It's going to hit this, that electron is going to go shooting off at some speed v, and then light will be coming off at a different frequency. I'm going to call it F2. I'm not putting a subscript here just to save myself time. I'm eventually going to get, well, I know that there's some difference between F and F2. And so this frequency coming off, I'm just going to say is equal to my initial frequency plus some change in the frequency. Delta F would be a negative number here, but I would keep it as plus delta F. So if light's behaving like a particle here, well, I've got a collision between two things. I got two particles colliding. What is the arrow in our quiver to handle things that collide into each other? From Physics 251.
Conservation of momentum.
Yes. Momentum is conserved here. So conservation of momentum. And we will also have conservation of energy. At this level, there's no friction, there's no air resistance. I mean, none of that stuff is existing. There's nothing that's going to dissipate the energy or the momentum. So, in order to resolve this, let us assume that the initial light wave was coming in at along this line right here, and then the light goes shooting off at some angle theta. Momentum is a vector. So what's the formula for momentum?
F
But what about light? Light doesn't have a mass. Well, if I think about that, I know that my energy of the light is h times f, which, if I equate that to mc squared, that means that I'm saying that light has an effective mass. It does not have a rest mass, but it does have an effective mass in the case of colliding with things. So my effective mass of the photon, with a little photon there, would be hf over c squared. If I plug into my momentum formula, I get my hf over c squared times c, which is just hf over c. So the momentum of light, if it is a particle, should equal, again, Planck's constant keeps popping up, times the frequency over the speed of light. You need to get in again? I'm going to step across the hallway. I'm just going to let the video run. All right, momentum, vectors. Let's do it. So I have some momentum initially, so the electron we're assuming is at rest, especially if you compare it to the light coming in at the speed of light. So my initial momentum looks like this, and this is the momentum, gamma. And it's going to be equal to the sum of the other two, so I should be able to add this right here, which is the momentum, once you do down like that, this is the momentum final of the light plus the momentum final of the electron, which is mv. This angle right here is theta. My right here, let's go for something brighter. This momentum is going to be hf over c, and this one down here is going to be my final momentum, f plus delta f, over c. And this is mv. All right, I have a triangle here, an angle theta. What is the relationship between my sides and the angle?
Cosines.
Yep. All right, so if I plug in the law of cosines, I'll start you out. M squared v squared, this is mass of the electron, equals would it help if I said it's the law of cosines is the generalized form of the Pythagorean theorem?
Is that m squared plus v squared?
M squared plus MV something plus.
Wait, I got m squared v squared equals what?
It'll be the hf over c squared, all squared, plus hf plus delta f over c all squared. And then,
All right, that would be, if theta is 90 degrees, Pythagorean theorem, but
and
it's
then
generalized.
minus hf over c times the other one times cosine of the angle.
This one piece, one piece, two. No, there's two in front. All right, let's just expand that, see if we can get it down to a simplified form. At this point, when I write m, I know I did m of gamma over there, or m of the photon. This is, from now on, m is just the mass of the electron. I don't have to keep writing that subscript. So I have m squared v squared is equal to h squared f squared over c squared plus h squared f squared plus 2f delta f plus delta f squared over c squared minus 2h² f, see, it's distributing f² plus f delta f over c² cosine theta. Taking a moment to step back and make sure I didn't do some careless error here. So I got the 2h², still multiplying f, distribute the f, got that. Okay, I think I'm good with that. Over here, I'm squaring a binomial, f² plus 2f delta f. Okay, I'm good with that. This is a 2 right here. Anyone see any careless error? Well, we'll eventually figure it out at the end. So I have m² v² is equal to, let's pull some stuff out of this. I'm gonna pull h² over c² out. h² over c² times, I have f² plus f² plus 2f delta f plus delta f² plus minus 2f² cosine theta minus 2f delta f cosine theta. So factoring h² over c² out. All right. If we work under the assumption that the change in the frequency is small compared to the frequencies themselves, then this term right here really gets dwarfed by everything else. So this is going to be, and you could factor f out, and then you'd have, then you have delta f over f, which would be small. So I'm just basically saying the change in delta f, or the change in f is small compared to the actual values of the frequency. So that's going to be close enough to 0, so we're going to ignore that. So I have h² over c². I have 2f² plus 2f delta f minus 2f² cosine